Hello, Professor.
Hello, Kia. Nice seeing you. Kia, thank you very much for sharing the video.
Okay.
I looked through it and it's really nice. You should publish it independently on YouTube if you didn't do so.
I don't have any YouTube channel. You can upload it in your YouTube channel.
I can put your name, but I don't want to steal your credit because
No,
if
it's not. It's not like stealing my credit. You can write here that my name.
okay.
It's fine.
But it's really good guidance, and I'll share. If you push me to do so, I'll upload it to my channel and share everyone in the class.
Then in the title you can write something or not if you want. Or upload it.
Thank you.
Because I promised you that I will make that video. That's why I did it.
You did well. Thank you. Yes, thank you, Sarah. Thank you, Lina. Nice seeing you, Laura. So, hope your weekend went well and you are not through the one day of the week since weekend you are not super tired and have some energy. So, there are two goals for today's meeting. One goal is to explain what is suggested for next homework number 5, and it is more practical thing that you all will do. It's more important. And secondary goal, so in some sense you can skip today's lecture completely. It will not change your well, since you're here you can sit and relax, but it will not, today's lecture will not add anything to your understanding of the main line of narration. It will be just a little, how to say, short story apart from the main line. Like when you drive the highway and see vista point for some sightseeing. So what I'm going to deliver after we speak slightly about the homework. The Hartree-Fock theory is based on several building blocks, and one of the building blocks was the antisymmetry of the wave functions later determinant. Last time I did declare these features. I did declare the principle and how to construct multi-electron wave function out of atomic orbitals. But some of you were asking, what is the reason, where this specific form of the antisymmetric wave function comes from? Or maybe some of you didn't ask it explicitly, but you may have some curiosity. So I will make a little demonstration showing where this functional form of composing multi-electron function out of one electron wave functions come from. But for continuation of our main goal, for continuation of the understanding of Hartree-Fock theory, it is not as needed. We just need to believe in antisymmetric wave functions. And to make, I'm going to play open cards. The antisymmetry style of the conversion from one electron wave function to multi-electron wave function comes naturally in the studies of the spin. So if we introduce concept of the spin and build multi-spin electron wave function, let's say just only 2 spins, then there is a equation that I'm not going to solve. I'm going only to declare and show it. But if one finds the eigenstates of total spin operator, the solutions of possible arrangements of individual spins into 2-spin wave function will show one single configuration and 3 configurations representing triplets. You may have heard it or got it in your in the past or future courses in quantum mechanics. As more frequent and energetically favorable singlet state composed of 2 spins, we will set up an analogy between two spin wave function and principle of antisymmetry wave function and Slater determinant. So here is the goal. And if you are really, well, of course I will be pleased if you stay and listen to me, but if you are really in a rush and you need to sacrifice one lecture, this is the one to sacrifice. Some other lectures will be more important. So a few words about the homework before we go to slides. The homework will have 2 components: the easy one and hard one. The easy one will be based on today's lecture, and if you just look through, yes.
I saw the homework is divided by 2 parts. First one, it's like a math. I can say that one is math. It's not pure math, but it's math. Okay. And then the second one, maybe we need to use software.
Yes.
Mobatic software. That one.
Yes. So I'll tell about both. For the first one, for the math part, yes. If you just listen to today's lecture in a very relaxed fashion, it will be enough information to do the first part in like 5 minutes. Okay. It will be really easy. Yeah. So if you look on it and it looks complicated, do not worry. It's some strange symbols, but I assure you that it's a very simple level. Do not worry. And if any problems appear, if you hate equations, just shoot me an email. I'll answer, and I promise it will be easier. Second one is not intellectually challenging, but it is laborious. So in our last lab, we did basically 2 things. First, we created a molecule like titanium hydroxide, and then we characterized it with the Hartree-Fock method. Yeah. Right? For the second part of the homework, we need to do the same for 4 additional molecules. So you need to, like crazy, build molecule, run Hartree-Fock, build molecule, run Hartree-Fock, analyze data. It's also will not take much of your time. It should be doable shorter than in 1 hour. Okay, but
the same thing like we did it before for 5 model, like monomer, dimer, trimer.
I'll show the slides in a minute or 2. But in the class, we worked with monomer. So the data for monomer can be just borrowed from the lab. Okay. You have structure, and we discussed characterization, like total energy, HOMO-LUMO gap, energy of HOMO, energy of LUMO, right? Mm-hmm. You remember it. What you are invited to do in the homework is to do the same steps for longer and longer molecules. And I invite you to carefully do optimization and maybe share with me intermediate structures. I may slightly help, because the electronic structure result may depend on how atoms are arranged in space. Okay. Any general questions about plans for today's meeting?
Oh, excuse me, Professor. For the homework, for the second part, what should I do that I don't have access to Gaussian?
Okay. So, how do you share file? You run some jobs on HPC, right?
Yes.
how do you transfer files between your personal computer and HPC?
I don't use my Mac. I use the desktop in the office. So I use
then use your desktop in the office for the homework.
Oh, okay. Okay, I'm using WinSCP in the WinSCP. Yes.
And you can use WinSCP to transfer, communicate with Photon, same as you do with CCast.
Okay, thank you.
And in your desk, in your like office, if you have Windows, you can launch MobaXterm there.
Yes.
We need to send request for that.
Yes.
No requests. MobaXterm does not need system administrator privileges. If you install it forever, yes, you need some system manager password, right? But if you just download and run, it works for everyone.
Okay, then we try. Sarah, we will try to.
Okay.
Okay, and I think I keep thinking of your problem, and probably I need to borrow somewhere a new Mac and try to resolve it, because I don't remember how I did it for mine. But one day we need to change. It should be some other privileges. If you look in forums or talk to some other Mac users, maybe someone will give suggestion. Do not take as a main goal of your life because you have PC in your office, but we will resolve it. It shouldn't be difficult. Just concentrate on it, maybe in a free time.
Thank you.
Thank you. Any other questions about general plans for today's meeting? Okay, then I'll start sharing a screen, and I will bring the slides. Picture 10. So next time when we meet on Friday, maybe we will make sign up list for the thing, and we will know majority of the subject. But right now let's skip it. So here is the homework, and during today's meeting I will explain meaning of each of these symbols, and it will take like if you are very slow, if you think you're slow, and it is very new material for you, you will do it in 5 minutes. If you have some concept, you'll do in seconds. So just little familiarity with these notations and scheme will help us through the class. And here is the second part. So before we go to this boring lecture material, I would like to tell what does it mean. So monomer, dimer, trimer, tetramer, pentamer. So we count how many titanium atoms are in this model. So first model, 1 titanium. Second model, 2 titanium. Third model, 3 titanium. And so forth. So they are connected to a chain, and the terminal parts, terminal elements of this chain are hydroxyl groups, OH groups, and if it is more than one, then we have titanium 2, so it's a linear chain. Let me quickly show. So here is the monomer, just by hand drawing. Here is the dimer, right? Here is the trimer, Here is the tetramer, and you get the concept, right? So a titanium is each titanium is connected to 4 oxygens. Each oxygen is connected to 2 titanium. And intermediate oxygens connected only to titanium, terminal oxygens connected to hydrogen. There is a little trick that you may miss. I just do not want you to miss it. So you see that one can draw a plane connecting 4 atoms: titanium, oxygen, oxygen, and these planes in the alternating things should be oriented by 90 degrees. If you draw it from the beginning, the optimization will go much quicker to more beautiful structure. If you draw everything in plane from the beginning, it may become ugly and corrupt, even if you optimize, come to wrong minimum. Okay. And here is the summary of what we did in the lab for monomer, single point calculation, energy for with hydrofob. Here is what you do if you do not have graphical access. You just create structure by other editor, transfer file, and then edit the input file. And after the calculation is done, you just analyze total energy and the border between occupied and unoccupied. Here is an example of a diamond. It's not a big deal, but just in case you feel discomfortable, here it's how it looks like. Right? So 2 titanium, 2 oxygen in between, and on the sides it's same as monomer. Any question about homework? Everyone is okay?
Dr. Kellen, so
Yes.
today you talk about the affinity.
Oh, yes, happily. If you look on this table of eigenvalues,
I just want to
take them
understand what's the concept of affinity.
I will focus on it more in the later lectures, maybe Tuesday of the next week. But here, just take as a definition consider energy of HOMO as ionization energy, and energy of LUMO, the first virtual, as affinity. The meaning electron affinity, that if you bring an electron from outside to your model, the total energy of the model will change by approximately by the energy of the orbital where we place this electron. So if this orbital is low enough, then it will be energetically favorable to bring an electron to chemically reduce the model. So it has affinity to accept electrons. If the energy of this level is high enough, then bringing an additional electron only increase total energy of the system, which means system does not want to accept extra electron, so it doesn't have affinity.
But can I say more affinity or lower energy in that state? It makes the element more active.
It's not. It's incomplete statement because chemically active molecule can be either oxidizer or oxidizing agent or reducing agent. So the one with affinity, it deals with reduction, and one with noticeable ionization deals with oxidation. Vola, would you please correct me if I told something wrong?
No, you're correct.
Okay, thank you. Among us in the room right now, Vola is most educated chemist, because she's in chemistry and all of us took some other subjects as a major. I took physics.
Engineering department, totally different.
Just take microphone closer.
I'm from civil engineering department, so I studied this subject when I was in college.
Okay, very good, very good. Then you also are an expert in oxidation and reduction. You also get a credit for it.
Me, I studied these things when I was in high school.
Okay, then you get a super credit because you knew it before all of us.
I'm actually not so far from you guys because my background was in chemical engineering.
But do you have more questions about the homework, or not? If you develop more questions, just send me an email or talk. I would be happy to talk privately. So here is I was trying to do this homework myself in the past, and before going to electronic structure, I was optimizing and working on the spatial orientation. But let's focus on the lecture material, on the spin and antisymmetry. So last time we met for the didactic lecture last Friday, we got this equation. So two functions for individual, for single electron wave functions, we can call them phi1, phi2, or f and g, and two electrons, first and second. If you make two types of this product where we swap the order of first and second electron, or we keep the order of electrons and swap the order of functions, then combination of these two products is what is needed for multi-electron wave function. So, and such practical composition will come to as a result if you compose a matrix where in the row we will change the function first and second, or f and g, and along the first column we change the electron first and second, first and second. So if one takes the determinant, then one makes a product of the things on the main diagonal minus product of the things of the subdiagonal. So f r1 g r2 first term, f r2 g r1 second term. Make sense? Okay. Now, this is only a practical recipe, but I'm going to give an example how one can derive this equation. And again, we do not need it to succeed to get great success in the class, but maybe some of you have curiosity. So I will introduce notations alpha and beta for spin. We will so it will be function f alpha, function g beta, and here is a spin 1, spin 2. And we will form multi-spin wave function consisting of spin 1 and spin 2 that will take this functional form. And based on the observation of the multi-spin function, we'll, by analogy, we'll promote it to any multi-electron function. So if I arrive to this slide, it will be a great success. Let's keep this. Okay. Maybe in the next slides I will redo this table in a little better handwriting, but this ugly handwriting sketch is a plan of our lectures for next couple of weeks. So our goal is to get an algorithm similar as we got the algorithm for geometry optimization. We need a similar style algorithm for finding electronic structure, for finding energies and orbitals by Hartree-Fock method. Last time, I think it was lecture 9, we got the concept of Slater determinant. In the next, next, we'll get the concepts of mean field, exchange energy, and correlation energy. And by combining maybe 11 plus 12, will give us the lucky number 13 with Hartree-Fock method. And today we deviate just to consideration of spin in order to justify Slater determinant. But it is a side project. So from now on, you can lean back and relax, and I will keep mumbling and will attract your attention when it will be something really important. Now things are equally unimportant. So in this chapter, we are focusing on the electronic wave function, where ions are nailed down to the space, and we allow only electronic motion. Then we remove nuclear kinetic energy and electronuclear and nuclear repulsion from Hamiltonian, and we have three terms. The wave function typically depends on several R1, R2, and so forth, positions of several electrons, R1, R2, and so forth. So several electrons. And we do want to have a protocol how to build many electron functions out of one electron wave function. Why we need it? Because it is the only thing we can do. The factorization, the representation of multi-electron wave function as product of one electronic wave functions is very doubtful, because there is a term that mixes electrons and nuclei. There are no, this one is good. Sorry. Yes. So we do have a term that mixes electrons, electron propulsion, which makes all electrons not independent. They depend on each other. And factorization is not the best idea, but it is the best possible idea. Through Slater determinant, we match antisymmetry, and we have the general protocol. Right? If the factorization is allowed, if we already have single electron wave functions, atomic or molecular, how do we construct multi-electron wave function? And the protocol, even if you have more than 2 electrons, is to form a matrix where along one axis we list all orbitals, all one electron wave functions. Over another direction, we list all electrons, and then we take determinant of this matrix. And then it will be accepted protocol to build multi-electron wave function that depends on several electrons, R1, R2, and so forth. This was not new. It was a summary of what we did last time. And one electronic wave functions for atoms have 4 quantum numbers: principal, orbital, magnetic, spin. And today we are going to focus on spin. So I'm going to say something that I suggest you never repeat in public. I'll say something wrong, which, however, will help us to understand material. So may I ask you what you are understanding? How do you define spin? What is spin of electron? Lina?
Yes, doctor. So the spin, so now we know that the electron is moving in its orbit, and while it's moving, it's also make a rotational motion around itself. So due to that, there is some characteristics, magnetic or electrical characteristics due to that motion, give a special feature for this motion, which can be described as a spin.
Excellent, excellent, thank you. Anyone wants to add or correct? No. Okay, so I was going to say the same with a disclaimer that it is a good starting definition, but it is, please do not repeat it in public, because it is, strictly speaking, it is wrong. I'm not criticizing you, because I was going to say the same, but for picky people, it is not correct in the following sense. If we assume that electron is a sphere with a given diameter, and it is all populated with minus charge distributed along this sphere, and we assume that it may rotate clockwise and counterclockwise, then rotating the moving charge creates magnetic field, and there will be magnetic dipole, depending on the rate of this rotation, right? And there are only 2 allowed angular velocities, angular momentum for these rotations. One corresponding to angular momentum h bar over 2, another is h bar minus 2, rotations clockwise and counterclockwise. So this is all good initial discussion, but strictly speaking, if one assumes that electron is a sphere with a finite diameter, then the surface of the sphere must move with a velocity substantially bigger than velocity of light, which would create a paradox and conflict with other theories. So the correct way of describing spin, so right now I'm going to say something that you can't tell in public. It is an internal degree of freedom of an electron that results in the angular momentum and magnetic moment taking values h bar over 2 and minus h bar over 2. So such definition is seamless, is okay to speak in public. So no matter how it is created, maybe something rotates, maybe not, but just angular momentum up and down, 2 values. This is good. So here are, let me ask if there are any objections or questions. No? Everyone accepts? Okay. Now there are notations. So if it rotates clockwise or counterclockwise, one can call it 0, alpha up, or beta down, beta down 1. So there are typical pairs of notations like plus and minus, 0 and 1, up and down, alpha and beta. And most typical notation in the computational chemistry is alpha and beta. So it's just a feature of the community. People tell like alpha spin and beta spin. In other communities, people may use different notations, like 0 and 1, plus and minus. But from now on, I will try to follow alpha and beta notations. May any one of us in class explain what are these angular brackets? Sarah?
No, I don't know.
Okay. Lola? Have you seen this angular bracket notations in the past?
No.
Kia?
No, I never.
Lina?
Yeah, I've seen them in the quantum mechanics class.
Okay, so can you explain what are they?
As I remember, if this notation plus that direction, the antisymmetric state would be in the opposite direction. I don't.
Okay, nothing wrong.
It's just demonstrate a state, a unique state for the.
Yes. So let me squeeze quantum mechanics class in 30 seconds. There are two types of wave functions. Typical wave functions and orbitals that we will draw are distributed in space. They depend on continuous coordinate, position of electron, like we put R on one hand. On another hand, there is a range of quantum problems, such as spin, or just set of already found molecular orbitals, where instead of coordinate, we use index of a quantum state. So the wave function is in such representation, instead of continuous set of numbers, it will be a vector of very small discrete number of values. And continuous function and a vector seem to be mathematically different objects. But in quantum mechanics, they both obey the same features. And this angular notation is used to represent both vector with elements like C1, C2, and a function like phi of R1. And this angular brackets is referred to as Dirac notation. So it is nothing else but just a wave function. There are some additional features which I'll introduce shortly, and I have a big hope that you will like them. And if you have teaching career components in your future, you're welcome to use following next slides and for your teaching. So, not this one. Next slide. So, if we do have spin, and independent of whether we agree or disagree with definitions, some of you may have practiced NMR experiment. Lola, did you?
Not so much, but yes, I know what the NMR is.
Okay, so the in NMR it is spin not of an electron but spin of a nucleus. For spin of electron it is EPR, electronic paramagnetic resonance, and NMR is nuclear magnetic resonance, also related to medical procedure of computer tomography when they scan the body with a contrast. So what we do is related to this application. So by external perturbation, by specific electromagnetic radiation, one can make the spin to flip, change its orientation from up or down, or from down to up. And if you want to introduce the math for this flip of a spin, we need spin flip operator that converts alpha into beta. So here is wave function for wave function of spin alpha, wave function of spin beta, and here is the operator. So this notation prompts details of the Dirac notation. Or I will introduce it in full details in a second. Did you hear about normalization of the wave function?
Professor, one thing that
Just show yes or no. Okay, so wave function must be normalized. So what does it mean? It means if you take wave function, multiply it by its complex conjugate, which is symbolized by star, and integrate over the area of definition, it must be equal 1 if it is one electron, or n if it is multi-electron wave function, number of electrons. So if it is one particle, it should be 1. It means normalized wave function. Make sense? Nothing complicated. No.
No, please can you say that again?
Please repeat, closer to the microphone.
I said, please, can you repeat yourself?
Okay. So any wave function must be normalized, must have a property of normalization. So if we take wave function phi of r and we take wave function phi star, which means if function contains imaginary unit I, which is a square root of -1, then star means flipping sign in front of I. For example, if wave function has a shape of e to the power minus I, let's say kx, and making star will flip the sign e plus I kx. So here is imaginary unit, and exponential is something that we all like, right? Because of calculus. So you see that here in this expression, we multiply wave function with star times wave function without star. So by notation of Dirac, wave function without star is called CHEM, and wave function with star is called bra. Why? Because these two types of wave function are always have to be multiplied onto each other and form a bracket. So bracket consists of bra and CHEM. Therefore, the thing without star is bra is cat, and with star is bra. Make sense? Okay, and I believe we are on the recording. You can listen to it, or it is quite general. You'll find it anywhere in Wikipedia or online, like bra and cat notation. So without star it is cat. With star it is bra. Now let's revisit the concept of operators.
Professor, here why you I'm not able to understand that before alpha why you wrote 0 here, why you write 0 here, 0 alpha, 0 equal to alpha, 1 equal to beta. Why?
Okay, I understand your question and I'm ready to give an answer. Let's flip a couple of slides back. So here, everything in the first line is the same. So those are alternative notations. So this one can call one state as plus or minus sign. By the way, it should be minus here. Minus 0 alpha down. So it's not 0, it's a quantum state number 0, lowest possible quantum state.
What does mean that quantum state number 0?
Like you can count objects starting from 1 with natural numbers. Here is my pen number 1, here is my pen number 2, right? But I can start using integers. Here is my pen number 0, here is my pen number 1. Okay? It's good that we discuss it now so that you do not get distracted in the future. And now I am going to make something that I hope you like, but it may throw your minds off for a couple of seconds. So quantum state wave function means that we do not move or change the mass. We do not remove or add an object. It means we just change how it is shaped out. Like if we are talking about quantum state of a molecule, it is the same molecule, same number of ions, same number of electrons, but we change the shape how electrons are wrapped around the nucleus. So a person, now let's make an analogy with in a human life. A person, the same person, may prefer to get up earlier or may prefer to get up later, right? And in the common language, there are abbreviations for such people. A skylark for those who wake up earlier, and an owl for those who get up later, right? You agree with these words? Okay. Now, if something happens, for example, if I need to pass an exam next day, I may change my habits, and I will be the same person, but instead of getting up later, I will get up earlier. So it will transform my state. Hello, Steven. Nice seeing you connected.
Hello.
Oh. So an exam for tomorrow for me can change my habits, and instead of O, I will become skylark or opposite. Now let's look on the pictures. So here is an O. Okay. Now here is my exam that I fear, like a wizard that makes hocus pocus and converts me into a skylark. Make sense? Any questions to this point? No. Okay, let's go further. Now let's describe the same thing on the math language for quantum mechanics. So here is the cat vector for when I'm an O. Here is the operator that changes my state, and here is the cat state of the skylark. So quantum operator changes the wave function, right? Okay, let's go further. Now, if I compare myself in the mode when I prefer to get up later, if I like compare myself with my own image, if I look at my photograph, me, it's me. If I multiply and integrate, it should be 1 because it is the same identity, same person. But in order to make this comparison, I need 2 copies of myself and a mirror image, right? Bra and cat. If I am in the mode to get up later, I can compare myself to myself, bra and cat, but I still get number 1 because it is the same person, myself. So here we did illustrate the concept of normalization. I just look in the mirror, compare myself to myself, and I get the same person. Right? Now, if I look at the photograph of myself before exam and after exam, I see it's completely different person. It's a different state. This one is happy, another is scary, or this one was sleeping well, this one was not sleeping. So their comparison will give 0. So it's although it is the same person, it is different states, different modes, right? Make sense? And whether I convert from Skylark to all or backwards, from all to Skylark, it's the still comparison will be 0. Now, concept of quantum operators. If I flip the order of bra and cat, if I put bra first, bra here, and cat there, this object with flipped order of bra and cat is dyadic product by math language and operator by quantum language. Let me show. So here is an operator that it gives details how I look into the mirror when I change, when I do not change myself, when it is a regular day, when I am an O. Here is an operator that changes the O to the Skylark. So the most important thing that we have bra in one state and cat in the other state. So if I take this operator, tell it is the wizard that tells hocus pocus, and I apply this operator to a wave function. Now we have 3 images of the wave function. 2 cats and 1 bra. Right? Now I invite all of us to look on this object in a different way. First, here we group 2 things that belong to operator and then 1 thing that belongs to the wave function. Okay? Now I'm going to regroup. I'm going to erase, and group them differently. I'm going to group this one and this one. So now if we look on this longer group with 2 objects, what is the procedure of convolution of meeting bra and cat of the identical wave function? Please answer.
Can I answer?
Yes?
So we said if they are identical, it's 1. If not, it's 0. So it's delta function.
But here they are identical, right?
So it's 1.
Yes. So it is 1. And if it is 1, we can remove this thing, right?
That bird.
Yeah. Are you okay, or you have question?
No. I'm okay with that.
Okay. So we can practice the convolution, practice the orthogonality, normalization, and replace this bra times cat by a number, by number 1 in this case. So we remove it, and the only remaining thing is a wave function cat in the Skylark state, right? So we show how the operator changes the wave function. And now, through the example of everyday life, we do have mathematical tools to describe change of the wave function. Any questions to this picture?
No.
Okay, so basically we are done quantum mechanics maybe in 15 minutes. If you need to take this course in the future, you'll get the same things, just with a little bit more details.
So you already showed the spin flip state, and so the homework part.
I'm going to apply this notation to spin flip.
Yes.
And although I really am emotionally attached to birds, from now on I will use symbols.
Okay.
Okay. Oh.
Yeah, now it's alpha beta.
So alpha times alpha is 1, and then we get beta. So
yes.
Spin flip operator acting on alpha generates beta.
Okay.
Okay?
Yes.
Make sense?
Yes, it makes sense.
So it will be part 1 of your homework, and
yeah.
You see, it's not complicated, right?
Yeah.
So, and there is a S minus which flips in the different direction, beta times alpha, and if you apply this S minus operator, S minus which like lowering, it converts alpha to nothing, because here we do have product of different objects, so it will be just 0, impossible. And if we apply it to beta, it will make alpha. It just flips the spin. So generally, spin is a superposition of states alpha and state beta, which means electron can simultaneously rotate clockwise and counterclockwise with probabilities in front of this amplitude probabilities in front of this wave functions. And this is another basic property of quantum mechanics, which relates to linear algebra that you may have taken in math classes. So superposition or addition of functions with different coefficients. And if this is the case, then probability that the spin is in the state beta will be C sub beta absolute value squared, or C star beta times C beta. And here is the normalization condition for general wave function. In the homework, there will be only pure states. So it's more for.
What is C here? C alpha.
Thank you. So C alpha and beta is probability amplitude. So it's prob amp. So amplitude. So it is a such number by taking square of which we get probability. And here I cannot do anything. It's just conventions of quantum mechanics. So if instead of probabilities we deal with like square root of probabilities with amplitudes, then a lot of helpful things are possible. So we need to use alpha, C sub alpha instead of probability. So another thing is to combine raising and lowering operator, minus and plus. If we multiply them, so here is the raising and lowering operators together. Just want to do this right and redo it. So this beta into alpha is lowering operator. This alpha into beta is raising. But if we write them in a row, we can look on a central part, which will have alpha bra times alpha cat, which is equals 1. And then we will get beta times beta, which is operator that does not change state if it was beta. And if we, so such operators are named projectors. So generally, if you speak about any spin, we should be able to describe bra, ket and bra of any spin with C alpha and beta and C star alpha and beta. And there is a typical operation to find expectation, so-called find expectation value of operator or convolution of bra, operator, and ket. And even if it is not something that you were doing before, we just literally plug in these notations into each other and process them by trying to identify pairs on bra and ket. I know that if you see it for the first time, you can approach the state of panic. Please don't. By now, you already got about enough information to get the homework.
Yes.
The rest will be more for your information. And if first, feel free to ask. Second, send an email if you want to discuss it after. So if one applies the things to general operator and S plus S minus, one will get probability that system is in the state beta. So and here I'm just showing step by step how this is obtained. We are already over the time, and I do not know your plans for the evening, so I'll try to speed up a little bit. So here the bra contains 2 terms, ket contains 2 terms, and operator contains 1 term. If you open brackets, there will be 4 terms. And if you plug in definition of the operator into each term, so here is the definition of operator. But if we instead look on the pairwise convolutions, so alpha times beta is 0. They do not coincide. Alpha times beta, and we need at least 1 to be equal 0 so that we remove the whole term. Alpha times beta is 0. It's also 0. Alpha times beta is 0. It's also 0. But here you have beta times beta equals 1. Beta times beta equals 1. Therefore, the answer for the whole thing will be C beta, C beta, which means probability that spin is in the state beta. Whew.
It seems like that it's our homework.
Homework will be, I think it is easier. I'll open it once again. And if you are interested in electronic paramagnetic resonance or nuclear magnetic resonance from theory part, one will need also SX and SY projections of a spin, which are here, but likely we will not use them right now. So here is a little dictionary how to interpret the notations of these wave functions and operators in the matrix form. So the wave function alpha is, we can define it as first element is 0, second element is 1, because there are only 2 degrees of freedom. It means rotate only 1 direction. State beta, we will swap 1 and 0. It will be 1 in rotating counterclockwise and 0 otherwise. Bra, instead of column vector, we just do row vector. If you have superposition, Then we add together this proportionality coefficients, probability amplitude, and we place them in the vector column vector. If it is bra, we will place these coefficients in the row vector. And if it is an operator, there will be matrix, depending where we change up to down or down to up. Everything is zero, but there will be one in either one of the off-diagonal corners. So this table is absolutely sufficient to do your homework. And I promise, if you remember how to multiply vector and matrix, you'll do it really, really quick. And now, most important thing, but I will jump over it in the quickest way. So, and better just listen to me and look at me rather than to look on the boring equations, because I understand if you do not, they may scare you at the first glance. Suppose that instead of describing one spin, which can flip or be somewhere in between, we have two spins simultaneously, right? So if we have two spins, and we need to construct a product of the wave function for one spin and another, right? In order to address first and second spin, I will add the labels 1 and 2 to the general spin wave functions that are composed of alpha and beta, C alpha, C beta. But generally, overall spin wave function should be a product of such single spin wave functions, first and second. If I open the brackets in this expression, then I will see that the result is composed of 4 terms, or we can say of 4 basis functions. So interpretation of these 2 basis functions is quite easy and pleasant. So first basis function is first spin is up and second is up. Okay. Now second one, first spin is up and second is down. Third means first is down and second is up. And the fourth one is both are down. So by the laws of quantum mechanics and linear algebra, general state of 2 spins is a superposition of all of this, like there could be probability of all of these 4 states simultaneously. And in front of this basis states, we do have expansion coefficients, C1, C2, C3, C4. So one of the problems that one can solve in quantum mechanics is to find what will be the values of these coefficients. And in order to find them, one solves the highlighted equation at the top. So eigenstate of the total spin operator. So the S capital square is total spin operator. Total spin. And S square lowercase is eigenvalue of spin. Eigenvalue. So this equation is similar to our time-independent Schrödinger equation, but instead of Hamiltonian and energy, we deal with total spin. But it's still a legitimate equation. So now I skip all solutions, skip the methods how one solves it, and declare only one solution of this equation. So since there are 4 independent variables, there will be 4 solutions, but I focus only on one. So, so one of the most useful solutions will be when first coefficient is 0 last coefficient is 0, second is 1 over square root of 2, and second minus 1 over square root of 2. So it appears from solution for eigenstates of total spin operator. Total spin. So how do we interpret this solution? And we are about done.
Yeah.
Please.
Yeah, so the solution here indicates the first and fourth states. It's not possible to occur. It's not possible to get 2 up or 2 down.
Yes.
It's possible to get 1 up, 1 down, even the first 1 up or the second 1 up.
Mm-hmm. Makes sense?
Yeah, so this is why we get the probability 0, the probability factor 0 in the first and the fourth state.
The exact solution of total spin operator is a little bit different from this general correct philosophical consideration. There are solutions when both spins are up, both spins are down, and there is also state when there is an up and down, down, up with a plus sign between them. But they will relate to so-called total spin equals 1, total spin to triplet state. But right now, we will consider only solution for a single. So we have 0 here, 0 there, and up, down, and down, up are contributing to solution with probability amplitudes 1/2 and -1/2. So if we look at this solution, and instead of spin up, we will tell that it is function 1. Instead of spin down, you tell that it is function 2. So we replace beta with phi 2, alpha with phi 1, and instead of just index of spin 1, you tell R1. Instead of spin 2, you tell R2. Instead of spin 1, we put R1, and instead of spin 2, we get R2. We will reconstruct the Slater determinant for two-way function. SD is not South Dakota, it is Slater determinant. Okay? I do not know if it is sufficient as an argument, but at least it gives, I hope it gives you confidence that this antisymmetry wave function can be derived rather than postulated. And by observing this symmetry from consideration of two spin 1/2 system, we arrive back to the antisymmetric composition of multi-electron wave function out of single electron wave function, or Slater determinant. So this part allows us to return to the general flow chart, and our next concepts will be mean field, correlation energy, and exchange energy, after which we will get to a flow chart in some sense similar to the flow chart algorithm that we use to optimize the geometry. Enough. I'm sorry for taking extra minutes of your precious time, but I'm done. Everyone is welcome to depart, disconnect, and I'll stay here to answer questions if any. And many thanks for dedicating effort to the class.
Thanks, Dr. Kellen. Have a good night, everyone. Bye.
Professor Kellen?
Yes.
I'd like you to pull up your slides. I have a couple of questions.
Okay. Should I bring slides up?
Yes, please.
Okay.
On slide 57, Yeah. So what's the difference between superposition cat and cat?
And bra.
Uh,
So here, superposition cat and superposition bra, these two.
yeah. Yes. What's the difference?
Okay, thank you for the question. I think I'm ready to answer. So just for notation side, here is the angle arrow to the right, here the angle arrow to the left. And the letter sigma means that it is any superpositional spin, which can be either beta or alpha or superposition between them. And this sigma is composed as summation of alpha and beta. If we have this angular bracket at the right side for superposition, we have also angular bracket to the right for the basis functions. If we have this angular bracket to the left here for bra, then for basis functions we also have this bracket to the left. Now, in addition, when we jump from cat to bra, we we not only change the notation of basis factor, we also change we add a conjugation. We put star on the top of this probability amplitude. So this little star means that, for example, if C alpha, for example, was equal I divided by square root of 2, then C star alpha will be minus I over square root of 2. And let me give another example, maybe more general. If our C alpha was, let's say, 1 plus I, then C star sub alpha will be 1 minus I. So the star operation flips the sign in front of imaginary unit and keep the sign in front of real numbers. This little for the homework you do not need it, but generally it is basic definitions in quantum mechanics. So wave function and wave function conjugate differ by this complex conjugation. There is one more difference between superposition cat and superposition bra. If you look on the third column here, you see here I write it as C sub beta, C sub alpha as a column, right? And here I write it down as C sub beta, C sub alpha as a row. So why do I do it? Why it's not me, I'm not taking credit for designing this notation. Why Dirac does it? So if I practice multiplication of vectors, if I do sigma bra times sigma cat, so it will be equals to vector row C sub beta star C sub beta sub alpha star times vector as a column C sub beta without star, C sub alpha without star. And now I need to practice the single thing that I remember from linear algebra class. How to multiply. Let me ask you, Lola, did you were you exposed to a little bit of linear algebra?
Yeah.
Okay, what is the rule how to multiply matrix by a vector?
So CB multiplies the CB star. I think I can't really remember, but like the individual elements, CB goes to CB star, and then C alpha goes to C alpha star.
Yes, and the general rule that I invite all of us to remember is row by column.
By column, yeah.
So first element in the row multiplied by first element in the column plus
It's
second
a higher math.
element in the row multiplied by second element in the column, right?
Yeah.
Okay, so now after this little exercise, yeah, I know, thank you. I'm getting a signal that I'm over time. The quantum theory was designed after linear algebra, and these notations were intentionally designed to practice row by column rule. So when we multiply this row vector by this column vector, we get a number, right? So it is a number, it's not a vector anymore. And this number, if the wave function is defined well, should be equal 1. It should be normalization. So the superposition ket and superposition bra are intentionally designed to be able to practice row by column rule, to be able to practice normalization, and to be able to practice convolution of vectors and matrices, quantum states and operators. Does it answer your question or make things more complicated?
Answered my question. Thank you.
Okay, thank you.
And then the other thing is, I looked through the assignment, and the first part, I'm still not sure that I can do it. Maybe if I watch the video again.
Oh, let's look on it and try to do it. Try to just start it. So let's take definition. What is, so first 2 questions about S minus. So you should scroll through the lecture and find definition. The S minus, and please correct. Let's just glance so that I do not violate. Yeah, we are almost ready.
Sorry, Professor Q.
Just a second. It's just a reminder for a little medication for the health. So, let's scroll through and find what is how did we define S minus? So we defined S minus as alpha times beta, right? So let's go to the last slide and just rewrite it. Alpha, beta, and the ket times bra, right? Now let's do this first thing. So we need to multiply S minus times beta. We plug in definition of S minus and write down alpha beta by definition times beta, right? Now we should refocus our attention and look on the last 2 things. So beta times beta equals what? Lola, please answer. Huh? Yes, 1. And we can cancel it. And then the result will be alpha, wave function alpha. So the first exercise is alpha.
Okay.
Make sense?
Yeah.
And so it took us maybe 20 seconds.
Okay.
So you do the rest really, really easy. Do not worry.
I think the
Yeah,
first
please put microphone closer.
Okay, sorry, Professor. The first part 1, for the assignment, it will be easy. I think
Closer.
the this homework, the first part is so easy. So I think we don't need to worry about this.
Correct.
Maybe Professor already explained it clearly.
And if you have any problems, feel free to send me an email. I will answer. And do not worry. You're not alone.
Yes.
Okay. Thank you.
Okay. Any other questions?
None. Thank you. Good night.
Oh, okay. Yeah. Thank you. And I really appreciate your investment of time into the class. I understand that there are some new concepts which could be a little bit away from your main goal, but later on, I hope it will help overall progress.
Thank you, Professor. Have a good
Thank you, sir. Yeah,
goodbye.
Good night.
Professor, I already complete the first lesson
Super. Okay, yeah.
because it was started to explain too hard, and then I thought that okay, let's do the assignment because it's so easy. You already explained the first part.
Thank you for
Done.
evaluation.
It's done. Okay, Professor. Good night.
Good night. Okay.
Professor, another thing, and
Oh, please.
in the lab, do I need to bring my laptop? Because
It's better, and the motivation is as follows. If you do things on your personal laptop,
okay.
You'll even better not Mac but PC. But the general motivation.
HP.
Yes.
I have 2 laptops. Okay, then tomorrow I will bring my HP laptop.
So if you just practice doing exercises on your personal laptop, then later for next exercises or research, you'll be able to do it independent of the class and any facilities, like do everything at home.
Okay, Professor. Tomorrow I will bring the laptop. Okay. See you tomorrow.
See you. Good
Bye.
night.
Good night.